Hi everyone, I am Mahesh. In this video, I am going to show you how to find a given number is a prime number or not. First of all, let us understand what a prime number is. So, a number can be called as a prime number if it is divisible by 1 and by itself. Meaning, if we have a number n, so if it is divisible by 1 and if it is divisible by n, then we call that number as a prime number. To keep it simple, a number, if it has only two factors, it can be called as a prime number. Examples for a prime number are 2, 3, 5, 7, 11, and so on. These are called as prime numbers, as these numbers has only two factors, are divisible by only one and by itself. So now let us write a Java program for the same. I'll create a class, we'll name it as prime number. Let us have the given value n in a variable called n, and for now I will have it as some 13, and then we wanted to find this number is prime or not. For that, let's create a method and pass this value into it. So we'll create a new method now. And let us say, for example, this method returns boolean. So it returns whether if n is prime, let's return true, or if the given value n is not prime, then we'll return if it is prime, we'll return true. If it is not prime, we'll return false. And how do we start? So as the given number should be divisible by, how did we define? So either it is only divisible by 1 and it is divisible by itself. So let's start with a loop starting with 2. As any number, as even prime number, it can be divisible by 1. So we'll start with 2 and less than n. Will not have less than or equal to n, as we know, like a prime number can be divisible by 1 and itself. So we'll start with 2 and we'll end with n minus 1. And what we are going to do is, given the number n, we'll divide it by the index I. So modulus I gives us the remainder. So if it is 0, then meaning that some number in between 2 and n minus 1 is able to divide n perfectly. Perfectly divisible in the sense it is divided perfectly with meaning it leaves remainder as 0. Then what we can say, we wanted to return this is false, meaning this the given number n is not prime. And we'll loop this. If you observe, we will loop this till n minus 1 numbers. And if it is I value is equal to n, and if it is not entering into this if condition, then we can conclude that it is prime number. So if you observe here, the loop starts with 2, and say for example in our case 13 percentile 2. So 13 percentile 2, what is the remainder? Remainder is 1. So in this case it is false. So I is incremented to 3. So 13 percentile 3. So in that case also it is 1. Remainder is 1. 13 divided by 3, remainder is 1. So this condition will be false. 4, it will false. With 5 also it will fail. This condition will be false. Likewise, it will still continue like till 12. I becomes 12. Even 12 can't divide 13. So we'll get the remainder as not 0. So it will never enter into this loop, and the for loop breaks, and finally it returns true. And we can also verify for any non-prime number as well. So for now what we'll do is prime, right? So it is returning a boolean value. So let's actually capture this into some boolean, or what we can do is we can verify the condition here itself like this. If it returns true, then we will say given n value is a prime number. We can conclude that. Else we can say that the given number is not prime. Given n is not prime. That's all. Now let us run this. So we can clearly see here 13 is a prime number. And if I give some number like 15, we can see here it clearly says 15 is not prime. As 15 is divisible by, we know 15 is divisible by 3, and also it is divisible by 5. So it says it is not prime. This is how we can write a program to find a given number is prime or not. Now we will actually optimize the code. So now at present we are actually iterating. If you observe, we are taking I value from 2 and we are continuing till n minus 1. So we are taking like almost like n minus 2 iterations to find a given number n is prime or not. Now let us try to optimize this code. For that, let me take an example. Say for example, if there is a number 31, or let us actually start with even numbers. So any even number is divisible by 2 clearly. So what we can do here is we can actually write a condition. So if a given number is starting itself, we'll check this condition, and what we can do here is we'll directly say it can't be prime number. As we can clearly see here, we are verifying the given n value with 2, like we are dividing it by 2 and we are verifying the remainder. If it is 0, then it is perfectly divisible by 2, meaning it is an even number. No even number is prime except 2. 2 is the only even prime. So here itself we can we don't even enter into the for loop. Here itself will return false, saying that the given value n is not prime. Till here fine. Now what we'll do is here, so anyway dividing it with 2 is covered here, so we'll start the loop with 3. So let me comment this line, and we'll start writing the optimized code here. So as we already covered dividing it by 2 here, we'll start I value with 3, and if you observe here, we are incrementing I value by 1 each time. So if you observe now, so first it actually divides the given number by 3. So if it is false, so then what happens? I is incremented by 1, then it becomes 4. But we don't need to divide the number by 4, as if it is divisible, if it is really divisible by 4, it would have been already divisible by 2 as well, and we have got the result here itself. So we don't need to like divide this number with 4, 6, 8, any other even number. We don't want to divide any the given number with any other even number, as the first even number 2 itself can do that job here. So and so we don't want to actually check the number dividing it by any even number. So what we can do here is we can just increment I by 2, so that we will only verify dividing the number by odd numbers. As the logic here is like, if it is really divisible by any other even number 4, 6, 8, 10, or any other number, then it will definitely be divisible by 2 as well, and will return false here itself. So we don't want to check that condition. That's the reason we are incrementing I by 2 each time, starting with 3. As we are starting with 3, in the next iteration it will become 5, and in the next iteration 7, like that. Only odd numbers so only odd numbers will be present in I at any instance of time, and with that value we are going to divide n. Till here fine. Now we'll come to this condition. So to understand like what can be the condition, now let's take an example. So if a given, let's try to understand this with an example. Let's say for example we have number 31, which clearly we know that it's a prime. So how to actually find the factors for it? So n percentile I, right? Meaning I into some multiple is equal to n. That's what we wanted to verify. In this case, say for example, I is, we are starting with 3, right? 3 into some multiple. So 3 divided by 31, 31 divided by 3, 10, right? So it has 3 into 10. The multiple is 10 here. Is it equals to 31? No. So what we'll do, we'll actually increment I by 2. So this time I becomes 5. 5 into how many times becomes 31? 6 times. But is it equals to 31? No. Now what we'll do, we'll take 7 as I is incremented by 2. So 7 into 4, we'll try that. So even that is not equal to 31. In any case, if it is equal, we can return it is not, it return false, and we can say it is not prime. But observe here what is happening. 9 into 3. So even like 9 into 3 is also not equal to 31. Then we'll take 11. 11 into, we 11 has only into 2, like 31 divided by 11, so it will have only 2, right, divisor. I am writing 12 here. Likewise 13 into, if you observe, 13 into also 2, and 15 into 2, 17 into 1, and from here it is 19 into 1. If you observe, all the other numbers will be like, all the other numbers I value will be having the other odd numbers, and the multiple will always be 1 here, and so on. Now if you observe, we don't want it to actually verify with 1, as we know, like we are even in the last approach also we start I with 1. So we can actually ignore this multiple of 1. So even we can consider these odd numbers as I value, and the right hand side number we'll call that as multiple. So if you actually reverse this number, it becomes 1 into 19. So 1 into 19 into 1 is also equal to 1 into 19. So 1 into, in 1 into 19 case, 1 is our I value, but we don't want it to verify I with 1, so we can ignore these two values. Then come to this 2 into 15, 2 into 13, 2 into 11. So we don't even want it to verify with 2. We already had that condition here, so we can ignore these values as well. Now come to this value 9 into 3. So what is again, we'll have this reverse 9 into 3, we call, let's read that as 3 into 9, both are same, right? 3 into 9. So in that case 3 becomes I. That case is already covered here. If at all it was divisible by 3, then here we would have got that result. So we don't actually need this as well. Then we'll come to this condition 7 into 4. If you observe, again we'll reverse this value, like 7 into 4 can be read as 4 into 7. So 4 into 7, and if you observe I value 4, so we are not even considering the even values here. If you observe, we are taking only odd values, so even 4 into 7 can be ignored. Now if you observe, we are left with only two cases here, either 3 into 10 and 5 into 6. So with this only two, we can actually conclude that a given number is the prime number or not. So if any of these two cases equals n value, then we can conclude that it is not prime. And if these two cases fail in the sense, if in these two cases, if the result is not equal to the given number, then we can easily conclude that it is a prime number. And if you observe here, how do we know we need to iterate for only 2 times? So if you clearly observe here, I value which is on the left side, if it is gone increasing, and on the right hand side the value is gone decreasing, is going like it is decreased every time. So we can clearly see it here. So if you observe, when I value and the right hand side multiple, here if you observe these two, I value is fine. So if I multiple is greater than I value, it is fine. But if you observe, I value is actually greater than multiple, or multiple is less than I value. What I mean by I here is all the on the left hand side, 3, 5, 7, 9, 11, all these odd numbers are denoted with I, and the right hand side number 10, 6, all 4, 3, all these I am calling it as multiple. So just for your information, now we'll see here. So where should we stop the iterations? That is what we are discussing now. 5 into 6. So this is 5. But when I value is increased, the multiple is decreased. And we can clearly see here, if I value is greater than multiple, we can stop the condition here. Till here it is fine. As these two cases, I value is less than the right hand side multiple. Till here we can loop it. Once I value is like greater than the multiple, we should stop it. We should not even, we should stop it at this condition. And to speak it like correctly, we don't even need this condition as well, 7 into 4. So we'll stop, we wanted to stop at this condition itself. But here, how do we know like whether the multiple is greater than or equal to I? So we will actually, it has to be, multiple has to be greater than I, but it has to be it has to be always greater than I multiple. So for that, but it should not be less than I. So as we should not be covering this case. So in between, what we can take is, we can take equality case. So it should be greater than definitely, and it should not be less than. So let's consider equality, like as this case. Let me put it here like this. This is I value into some multiple. Now we want, what we wanted to do is, let's make this also I. Till here we'll actually iterate the loop. So say for example, when both becomes equal, we'll stop the iterations. So as the right hand side multiple should not be less than the actual I value. Multiple should always be greater than. Till that condition we wanted to loop, and for that we are taking the condition as, we'll stop the iterations when I value becomes equal to this multiple becomes equal to I value. So equals in the sense I, right? So I into I. At this condition, we'll stop the iterations. So let's write this condition here now. We can conclude that when I into I is less than or equal to n, till here we will actually iterate, and we can conclude. We can actually conclude the result. That is what we have seen here, and I wrote the same condition here. If you observe. Now, if you observe, it is I square equal to, I into I is I square less than or equal to n, meaning I less than or equal to square root of n. And how do we calculate the square root in Java is sqrt of n. This is how we can find the square root. So as I square less than or equal to n, we wanted to calculate I. So I can just write I less than or equal to square root of n. Or if we feel like every time this is calculated, what we can do is, we can just take this above here and have this square root of n, and we'll have it here, and we'll add the casting. We'll typecast this to integer, and we'll have this variable here. So what did we do here? First we started with like, if it is even number, here itself we'll return, like we'll divide that number with 2, and we'll check that if the remainder is 0, here itself we'll decide that that is not prime, as that is an even number. Then what we'll do, if it is not, so it is an odd number. Now we wanted to find if it is prime or not. So how do we start? We started with 3 and we increment the value by 2. So we wanted to only divide the number with odd numbers. And then the condition, we have seen the logic here, how to find the condition. So we'll actually verify till the square root of the given number, and the inside condition will be same. We will not change this condition. Now let us verify this. So the same, everything remains same. Just will run this, and we can see 15 is not prime. We can also verify for 31 as 31 was what we tried in the example, right? So you can see it clearly here. 31 is a prime, and we can try any other number as well. 77. 77 is not prime, as it is divisible by 7. Now just to like confirm the how like iterations, number of iterations, in how many iterations we can do this. So let's actually calculate the how optimized this, the second approach is. So for that, let me actually declare a variable called count, which is assigned to 0. For each time when it enters into the loop, we'll increment the count and we'll print the value. So number of iterations is count, and then it will just return false. So as it returns false, when it doesn't enter into this loop, we will not get this statement. So let me put it here as well, the same statement. Now we can see, so we have 77, right? So let's see here. So 77 is not prime, and we found that in 3 iterations. So this is fine, right? Like, and if we take this out, if we comment this out and compare this with the first approach, we can see it here. So it took like 6 iterations. And let us give some big value like something like this, which is prime number. And we can see it here. This big number like 4111 is a prime number, and it is taking iterations almost like 4000 plus 4109 iterations. Now let us execute the same with the second approach, optimized code. And we can clearly see here number of iterations required were only 31. We can clearly see how optimized the second approach is. So this is how we can actually verify with any n value, which is an integer. We can actually verify if that n value is prime number or not. So in this video, we have seen given a number n, we can actually find if it is a prime number or not in 2 approaches. We started with the naive solution first, and then we saw the optimized solution as well. That's all for this video. Thanks for watching.